For the recording, let me repeat what I said. Sorry for being boring again. But anyway, dy dx equal to f of xy is what we want to solve. This is the ODE. We want to solve it under these initial conditions, or this particular initial condition, and that's why it's called an initial value problem. And your job is, given yn, you have to find out yn plus 1, the next value of y. Of course, by the time you have gotten to yn, you have actually started with x0, y0, then you have found out x1, y1, x2, y2, and so on, right up to xn, yn. And you want to find out yn plus 1 equal to yn plus some additional term. Now, this additional term is always basically yn in all algorithms is basically the step size h times some kind of slope. When I say some kind of slope, of course, it means some value of f of xy which you have calculated by some algorithm, which is supposed to reflect the average rate of change between xn and xn plus 1 accurately. Okay. So just to remind you, in all the previous algorithms, the one we did last week, what we really did was we found out the slopes in between xn and xn plus 1 at several points and weighted averaged them, and that gave us my new yn plus 1 from this formula. But the important point that these methods, the Adams, Bashworth, Moulton methods make, is that since you knew all of these while getting to yn plus 1, you also know the value of the slopes at all of these points. In fact, you can actually calculate them and store them in a list, perhaps, and use them when you want. Is that okay? So these are already known to you. So these are slopes not only at the last value, which is the one which you would usually use in all the methods, right? In Euler, modified Euler, whatever, Runge-Kutta, you would have to use the slope at the beginning of the interval. X and yn is where this interval begins, right? So this is one slope we would have used in all the previous methods as well. But in the previous methods, you simply ignored all information about the slopes that you had before you got here. So what these methods try to do is use the slopes that you had already calculated on the way, rather than calculate new slopes. Okay, calculating new slopes, of course, takes time, especially if calculating the slope is if the slope is a complicated function, which might very well happen. Okay, so what you could do is you could use some of the previous slopes. In fact, you would use something like this. Sorry. I think I have messed up the notation somewhat. Let me just check whether. Okay, how do I find out the notation? Yeah, let me see whether this was the same notation that I used last time. Oh, this is actually all right, except that I used a slightly different labeling. So let me just change the labeling that I did use there. The claim is, let me just change the setup a bit. The setup is simply this, that I have actually calculated up to this stage that in xn minus 1, yn minus 1, and I want to calculate xn, yn. Xn, of course, is trivial, it's just xn minus 1 plus h. But I want to calculate yn from here. So this way, at least, Of course, it's the same thing as what I said, but it will keep the notation the same as last time. So it's better to do it that way. So let me just start over from here. It's of course nothing new. Is all I'm saying is I've got to yn minus 1. Now I want to find out yn. And this is going to be yn minus 1 plus an estimate of the slope, which is beta 0, f of xn yn plus beta 1, f of xn minus 1, fn minus 1, sorry, yn minus 1, up to beta k, f of xn minus k, yn minus k. And the job is to find out these coefficients beta 0, beta 1, beta 2, beta k. Okay? And well, this is the Adams-Moulton. The Adams-Bashforth simply doesn't have this term. In other words, Adams-Bashforth is actually explicit. That is, once you found out beta 1 to beta k, these coefficients, Adams-Bashforth just gives you a prescription for calculating yn from the previous values. Whereas Adams-Moulton, the one I've written down right now, actually is an implicit method, because here yn is appearing on both sides of the equation and you would have to actually solve for yn if you just use Adams-Moulton. So any questions so far? And it's easy to see that all I really have to do is actually do the derivation for Adams-Moulton, and then in the end, if I put in beta 0 equal to 0, then I'm done, right? Then I immediately get Adams-Bashforth out of it. So how does the derivation go? The derivation essentially goes this way. This equation simply means y at xn minus y at xn minus 1 minus beta 0 f of xn yn this thing should be 0, right? Of course, this thing should not really be 0, because y at xn is really y at xn is the actual value of y at xn, whereas yn is our approximation to it, or our estimation of it. So what we would expect is this is almost 0, right? And the important point is this will of course depend on the size of h, and the larger the number of small powers of h that I can get rid of in this expression on the left hand side, the closer this is going to be really to 0 for small h. Okay, so now I have two choices. I can use a compact notation, or I could use the thing written out explicitly. So let's try the compact notation. Okay, so y at xn minus 1, this quantity is actually sorry. Okay, is everybody okay with this? Is it correct even? Actually, it's not correct, by the way. So there are several errors here. So I would ask you to tell me what those errors are. I hope I'm still here. Yeah. So tell me, what are the errors here? I hope everybody recognizes what I'm trying to write down.
Sir, L will be from 1 to infinity, not 0, because
Okay, that's great. The zeroth term is already this one. Okay,
uh,
zeroth term is this one or this one? Which one?
xn minus 1 is the 0th term. So xn would be x1.
So you're saying this is the zeroth term,
Yeah,
right?
yeah.
Does everybody else agree here? This is just Taylor series, right? Nothing else. So what I'm asking you is everybody okay with the statement that this is the zeroth term of the Taylor series which you have moved to the other side? And so, as was rightly said, the series should start at 1. Is this at all correct? So nobody has an opinion about this? If you think it's correct, say so. I guess it might be. How do I know? By the way, if this had been the zeroth term of the Taylor series, then let me tell you exactly what you would have. You would not have a minus sign here because you're going from xn minus 1 to xn. That means you're increasing x by h. So that's going to be plus h, number one. And more importantly, or equally importantly, this wouldn't have been xn, this would have been at xn minus 1. Right? That's how Taylor series works, right? You find all the derivatives of the function at this particular point. That helps you to find out the derivative, the value of the function at the next point. Everybody okay with this?
Yes, sir.
Okay, so if we are writing this, which is I'm using the fact that I'm taking all these derivatives not at xn minus 1 but at xn, then this is really not the Taylor series that you were thinking of. It's actually slightly different. It's actually the Taylor series done at yxn, where you use minus h as an increase in x. Right? Is it okay with everybody? Just like when you go from xn minus 1 to xn, the increase in h is plus h. When you go from xn to xn minus 1, the increase in x is minus h. Okay? And that's all we have really used here. But there is one more thing which is wrong about this expression. So I want you to tell me what. In fact, it should be obvious from what I have said a while ago. While ago meaning right now, by the way.
Hello, sir.
Yeah, tell me.
The two-factor coming, no, sir.
What? Sorry, I couldn't hear you.
Outside the summation,
Outside the summation, what?
when 2 into summation, L equal to 1
2
to
into. No, it's not 2 into. This is just Taylor series. Why should there be a doubling?
due to
The
the
answer simply is there should be a minus sign.
minus.
All we have, okay, the point is what we had figured out is this, yxn minus 1 is actually L equals 0 to infinity minus h to the L by L factorial yl xn. Everybody agrees with this one? Yes?
Yes, sir.
Okay, so if everybody agrees with this one, you should realize that the zeroth term of this is actually YLXN, which if you take to the other side, you get this. Okay? That's exactly what we had up there, except that we had yxn minus yxn minus 1 on the left. That's why you have an extra minus sign. Okay, so that's all there is to it. This is just simply Taylor series, but it's actually called a backward Taylor series because you are essentially finding out yxn minus 1 from what you know about the function y at xn. You're going back, you're not going forward, which is why all the data that you are using, all the derivatives you are using are at xn, not at xn minus 1. Okay? So this is just the Taylor series used backwards. Let's put it that way. And all these terms that we are using here in between, other than the yxn minus 1, which is equal to this, any terms, let's say the ith term here is beta I times f of xn minus I yn minus I, right? Once again, what I'm going to do is write everything in terms of what is happening at xn. Notice that f of xn minus y, yn minus y, I is really the derivative of y at xn minus y, yn minus I. Right? Is that okay? That's what f is. So, first let's figure out what this derivative should be. Or, sorry, I messed up the notation a bit. Let me just go back. It is f of x, so I messed up this notation. It's not the derivative of y at xn minus 1 and y, it's the derivative of y, the function, at xn minus 1. Sorry, xn minus I, right? That's what f of xn minus y, yn minus I is. When x is xn minus y has a derivative. That derivative is given by this function, f of xn minus I, y of n, yn minus, and yn minus I. Okay, so this is what you really want. But what is y at xn minus I? That's, you tell me, what is that going to be? Again, Taylor series in terms of whatever is happening at xn. 0 to infinity, nth derivative of y at xn. What should I put in up here?
minus IH.
Yeah, minus I times h. That's a step to the power L. Okay? Right? Is it okay with everybody? And what should the derivative be? So when you do a derivative, what are you really going to change? You're differentiating with respect to the argument, right? So in this expression, Are you going to change the xn or are you going to change the h? Come on, the silence is a bit too deafening. This is elementary mathematics. I'm not asking you anything more than that. Say, okay, let's put it this way. Y at x plus h is what? Is y at x plus h times y prime at x plus h square by 2 factorial y double prime at x and so on. Okay? Clear? Now, there's nothing to be clear about. This is just the Taylor series. So y's derivative at x plus h, what is that going to be? So let me write down two alternative expressions. This one, where I actually differentiate these y's actually, and the other one is where I differentiate with respect to h, which is I get y prime x. They differentiate this with respect to h. Then I had an h cube by 3 factorial, differentiate that with respect to h. Are both of them equally correct? In fact, are both of them the same thing? I think we are just wasting too much time over very trivial issues. The easiest way to think about this would be simply to think about it this way. Y, forget the Taylor series of y. Think of the Taylor series of y prime. You want this, right? So it really should be y primes, sorry, y prime Lth derivative done at xn. Is that okay with everybody? So let's forget about what I said a while ago. That was also correct, but this one should be easier to understand. Is this okay? Come on, give me something. This is simply the, okay, Shuprabha said yes, but if somebody has not failed to understand this, please let me know. This is straightforward. All we are doing is using Taylor series not for y, but for y prime, which we can always do. Of course, it's valid for all smooth functions, which of course means that this derivative here is the L plus 1th derivative of y at xn, right? So if you plug the two things together, I hope you have not forgotten what we were doing. This was the expression which we wanted to put almost equal to 0, as close to 0 as I could. So what we are doing is we wrote down then we had this I equal to 0 to k, beta k, This is what we really had, right? Xn minus k beta, sorry, not beta k. This was the expression which we were trying to make as close to 0 as possible. And this thing, remember, turned out to be y prime at xn minus I. And y prime at xn minus I, we could just write as this. So if we plug that in, what I'm going to get is I'm just running out of space here. So what I will do is I will just write the second term. Leave the first term as it is because that's, of course, already something we have already handled. This one is going to be sum over, if you just write down this piece here, this is actually sum over L equals 0 to infinity minus IH to the power L by L factorial Is everybody okay with that? I'm just replacing the bracket here, which is either this, also it means this. It can also be written like down like this. Hello? Hello? Good morning. Arjun Kishore. একটু আমি আধ ঘন্টা পরে ফোন করছি। Okay, is everybody at all following this, or are we simply making it more complicated? We just get rid of this and push this in there.
Sir?
Yeah.
Sir, may I confirm something?
Sorry, my earpiece came off. Could you just repeat that?
Sir, may I confirm something?
Yeah, go ahead.
Sir, in that I shouldn't there. Okay, sir. You have given already. No, it's okay, sir.
Is it? I hope.
Yes, sir. The summation of I, that was I was talking. It's okay, sir.
So everybody's okay with this much? Now, all you have to do is just match the coefficients of the various derivatives of y. Remember, yl comes with h to the l here, right? And here, what does yl come with? Sorry, I missed out that there is an h in the front also, right? Because h times the slope. This is the average slope weighted by these various factors beta I. So what should yl come with here? The nth derivative? What power of h? This yl plus 1 here is multiplied by what power of h first? Yes? That's something you can see here. What is the power of h which multiplies yl plus 1? L plus 1, right? It's L plus 1. And so basically whatever derivative you have, here also yl came with hl. Here yl plus 1 came with h to the L plus 1. So basically you have yl to the power hl in all these terms, right? In fact, to make it more obvious, what I will do is I will just push this h, which is the step size outside. First, let's push it inside. The next step would be to use our very standard result that we have always used in power series manipulations. Make everything h to the L. That is, I replace L plus 1 by L throughout. So what happens? This L plus 1 becomes L. This L plus 1 becomes L. This L becomes L minus 1. Any other changes? Any other changes apart from anything else? All this. Good. This. So Aniruddha is saying that the sum should start from 1. Great. Right? Because if you have moved your index L down by 1, you have to ensure that the sum starts at the same place. So the starting index should go up by 1 so that the sum actually starts at the same place as it was doing before. So now this is pretty straightforward. All you have to do is combine them together. Right? If you combine them together, what you get is minus h to the power L yl xn times minus 1 by L factorial Is that okay with everybody? All I've done is just taken minus h to the power L yl common out. This of course summed over all L from 1 to infinity. So I want to make this as close to 0 as possible. But what I will do is I will try to ensure that for the smaller powers of h, all these coefficients vanish. Okay? And that of course means that this expression ultimately we will be left with only very high powers of h, which will give you an estimate of the error because you really want it to be 0, right? Is that okay? And so the equations that we wrote down earlier is actually these are very simple equations. These equations really are 1 by L equals sigma beta I to the L. I wrote down the equations wrong last time. Let me just point out what the equations really are. So I think it was Shayan who pointed out that the equations I wrote down last time were not even consistent, that they were not. Because I copy pasted this expression and used it throughout. But what you really have is beta 1 plus 2 beta 2 plus 3 beta 3 plus 4 beta 4. In the next expression, you have beta 1 plus 2 square beta 2 plus 3 square beta 3 plus 4 square beta 4. The next one is beta 1 plus 2 cube, 3 cube, 4 cube. Of course, this is also 1 cube. The pattern is pretty straightforward. Okay? Is that okay with everybody? This is essentially the set of equations to solve for beta 0, beta 1, beta 2, beta 3. And all you actually use in the derivation is simply Taylor series. The only difference is I'm using Taylor series in the backward direction as opposed to the forward direction, which we usually use it in. Clear? Or are there any confusions about this? You see that these equations are simply this equation written down in full. And I, of course, goes from 0 to infinity, 0 to k. So let me just show you how you would code this. And let me just show you a piece of code which I wrote down in the morning. I hope I've got it right. So I'm calling it predcore simply because it's a predictor corrector method. So that should be sort of clear from from the code itself, what I'm doing. Okay. It's another longish code because it does several things. Okay. Ignore the first part for the time being. The actual work starts here. Of course, you have to import NumPy and all these other standard bookkeeping stuff you have to do. But here I'm simply solving this equation f of x comma t is that is dx dt is minus x squared times t. Okay, so that's the equation. And that, of course, has a very simple solution. And this is subject to y at 0 equals 1. So this is 1 by x is equal to t plus a constant, t square by 2 plus a constant. And the constant is easily seen to be 1. So x is 2 by t square plus 2. Okay, that's the equation that you're solving here. Okay. So the code up here should be pretty familiar to all of you. Right? What is this? It's just a standard Runge-Kutta fourth order. Now, why do I have a Runge-Kutta fourth order code at all here? The answer is that in order that you start the method, you need k previous values, right? For the Adams method, any of these Adams methods to work, you need previous values, k of them. Okay? Because you need k previous values, you have to get them from somewhere. So you start the method essentially by doing Runge-Kutta fourth order, because we want it to be reasonably accurate at this stage, to calculate the first 4 values. So this is what you do. You first start with an empty list. Okay, I'm using Python code. I'm pretty sure those of you who do not know Python should be able to sort of follow. We are starting with an empty list here, and I'm running a loop k times, updating x and t using the Runge-Kutta update function, and just appending the values of the derivative f of x comma t, which since every time I calculate x and t, I get f of xt, which I store in a list. So what I've done is I've stored k of the first derivatives in a list fs. Is that okay?
Okay, sir.
Is it okay with everybody? And then I'm just changing it into an array simply because I want this. Well, what I want to do is use NumPy array code, which is faster and which is also much neater to write. So I had a list of the derivatives. I'm just changing that to an array. Then what I do, this is the Adams-Bashforth part. You just use the Adams-Bashforth calculation to add to H. This np.fs comma cab actually does exactly what dot should do. It does the dot product. You have 2 arrays. One is called fs, which is the derivatives, and another is called the cabs, which are the coefficients you need. Okay, so you just take the coefficients, you dot that with the fs. That means you essentially doing the c1 f1 plus c2 f2 plus c3 f3 thing. You multiply that by h, add it to x, you get your Adams-Bashforth estimate. Of course, now that you have a new h, what you need to do is to actually change the list of the f's that you have. Is that okay with everybody? You actually have a list of f's. Okay, so what you did was, what you had at this stage is f1, f2, f3, f4, let's say. I've used it to calculate x5. Next time around, am I going to use f1, f2, f3, f4 again? Or what should I use? Which f should I use? Yes? So when I want to calculate x6, will I use f1, f2, f3, f4 again? These are the 4 previous derivatives whose averaged, in some sense, I used to calculate x5. Will I do the same thing again? That is x5, x4. Actually, it's beta 1, f4. Beta 2, f3. Right? This is my xn, this is my xn, this is my xn minus 1. And what I want is beta 1 times f at xn minus 1 tn minus 1 plus beta 2 into f at xn minus 2 tn minus 2 and so on. So this is the last one that I have. This is the previous one, this is the previous one, this is the previous one. When I calculate x6, which f's will I use? I'm not very sure why this is so confusing. Is it confusing at all, or can you please speak up, because I can't really see whether you are following this at all or not. Do you understand what I'm doing here? I'm just using some notation which tells me I have 4 previous slopes, which I'm averaging in some sense. I'm multiplying by coefficients and adding up. And then adding h times that, of course, there's an h here, to the current value of x to get the next value of x. Is this part clear to everybody?
Yes, sir.
So the question is, if I want to get x6, what should I do? Should I use f1, f2, f3, f4 again? That is
F5
x6
to
would,
F2.
so I would use f2, f3, f4, f5, right? No.
Yes, sir.
So what I need to do is, I had a list of these 4 numbers. I will get rid of this number from there and bring in f5 at the end, right? Is that okay? Everybody is following me so far? Now, how do I get rid of a number from the list? How do I add one number to a list? That's easy, right? How do I add f5 to the list? What would I use? What Python command would I use? This is, of course, for those students who have
Append.
already done Python. Of course, you could use append. But if you use append, you will not end up with a 4-element list. You will end up with a 5-element list, right? So how would you get rid of the first element, the 0th element? One possibility is take a slice, of course. The other possibility is use something called a pop. But there's something rather problematic here. The problematic thing is, if you can take a slice perfectly well. The only problematic thing is, what we are dealing with is an array and not a list. While that has huge advantages while calculations are concerned, the trouble is array sizes cannot be changed. So what we did here is we sort of cheated a bit. I first converted the array back into a list, took a slice. 1 colon means drop the 0th term, take the rest. Okay? To this new list, I appended this term. These append only works with lists, not with arrays directly. And then I converted it back to an array so that I can use it again, over and over again. As simple as that. But the Adams-Boulton basically is this. All I did was, once I've got this Adams-Bashforth estimate for the x at the nth position, I then use that. Now I also put the slope at the nth position in my list of arrays. Then I use this new slope to calculate the x. You don't use the original slope, you use the new slope. In other words, what I'm doing here is simply I'm using the Adams-Bashforth to predict what yn is going to be, and then use the predicted yn and Adams-Moulton to find out the new yn. Y here of the x here is of course y. Is that okay? Did you get that? This is all I did. np.append works with arrays. You're right. np.append does work with arrays. The only problem is np.append is slow. Although, because look, the real problem is np.append actually does what I did here. So if you want your code to look neater, you could of course use np.append with arrays. Remember, the whole basic advantage of an append or using an array is that arrays already has fixed sizes and fixed memory locations. If you're using append, the whole list has to be written somewhere else, which is whole array has to be written somewhere else, which is actually pretty time consuming. In any case, I'm not sure whether that's going to be any worse than this. So you could actually use np.append. You could take a slice and append it and then change the array that way. Okay, that's a possibility. That definitely is a possibility. But is the predictor corrector approach clear to everybody? What I need for Adams-Moulton, okay, let me just go back to the slide. I think that should be sort of obvious here. So this is I'm just using the predictor corrector approach here. What I'm saying is I'm going to use Adams-Bashforth, which is this thing, to predict what yn is going to be. And why do I need that? Because in Adams-Moulton, I actually need yn. Remember, Adams-Moulton by itself is actually an implicit method. You have to solve this equation to find out yn, which often is very, very tough because f of x and yn may be a bad nonlinear function. Solving this equation for yn is tough. Instead of doing that, what we are doing is we are predicting it yn using Adams-Bashforth, using that in Adams-Moulton to get the stability of Adams-Moulton. So your final prediction for yn will be based on Adams-Moulton, but you would actually be using a hybrid approach. You would predict using Adams-Bashforth, then you would correct the result using Adams-Moulton. And that is exactly what one of the approaches of using the Adams methods. You could just use Adams-Bashforth on its own. You could just use Adams-Moulton on its own. Okay. So I will just take a minute to show you how good the result or how good or bad the result here is. Let's just try running this program. So this was written for arbitrary order because at the top of this program, there is actually a code which I didn't show you, which is how to calculate how to solve those equations and calculate the coefficients themselves directly, which is essentially using NumPy's solve option. And these are basically the coefficient matrices, the coefficients of the equation that you have to solve, and these are the coefficients that come out of it. Anyway, this program actually wrote its output for the differential equation in. Let me just check one thing first. H is 0.1 now. That you would all agree that 0.1 is really a pretty large step size, right? And let's see how good the answer is going to be. So this actually wrote the output in a file called pretcore.dat. So this is what the output looks like. Now, Just by looking at what the output looks like, there's absolutely no way to say how good this is. This could be complete junk for all you know. Okay, but we do know the exact answer. We know that it's actually 2 by t plus 2. So in GNU-plot, I hope all of you know this, that the variable has to be called x. So this is so let's see. Is this any good? It's not. Why not?
So that should be x square plus 2.
Oh, yeah, 2 by x square plus 2. Of course. Good. Thank you. Let's see. Yeah. Looks pretty good. At least you can't even perhaps see the line, or you can see the green line, cyan line, and the blue crosses, right? I hope. But does this tell me whether the error is big or small? Yes? Just plotting this graph, does it tell you anything about the error? It doesn't really, right? Because the point is that the scale of, if the error is say 0.01 or 0.001 or 10 to the minus 6, you will not be able to tell from this graph, because at this scale, 0.01, 0.001, all of them look like 0. So the line will pass right through the points. To see the error, what you really need to do is plot the error. And one way to do that would be using the using command in Python, in GNU+, sorry. I'm just going to plot, there are many errors, right? One error at every data point. So I'm just going to plot all of them. I hope all of you remember this much GNU-plot. All I'm doing is I'm saying use the data in the first column. That is, of course, the t values. And use this expression, which is take the data in the second column, subtract from it 2 by square of the data in the first column plus 2. So this is just 2 by t square plus 2 that I've calculated. Let's see what the error really is like. Okay. Looks pretty huge, but if you look at the scale here, can you see the labeling here? Can you see the number which is written here?
No, sir.
You can't. So let me just read it out for you. You should have to write your own program. And so this is 2 into 10 to the minus 6. That's the peak value of the error that you're getting. Note that the slope is only, the step size is 0.1, and you're getting a slope, getting a peak error of 10 to the minus 6. Okay, just to see whether our prediction that this is a fourth order method really is correct. Let me just change this to 0.01 and run the program again. And let's plot the error again. Now, this error for a smaller value of h actually goes the other way. But we are really interested in the absolute size of the error. That was 10 to the minus 5 order. What is the error here? It's 10 to the minus 9 order. So the error has fallen by 4 orders of magnitude because you have cut down slope by a factor of 10, which is exactly what a fourth order method is supposed to do. So this really is a fourth order method, and actually it's pretty easy to code. All you have to remember is just keep track of the last 4 values, and you keep on using it over and over again. And okay, well, I think I will take my word back about using numpy.append. You can use numpy.append. It should not really make it any worse than this one is. It will make the code a bit easier to write, I guess. One less step. Okay. Now, I'm actually out of today's time, but if you will give me 5 minutes, is there a class right after this?
Yes, sir.
Okay, then I think we'll have to go. Okay, let me just call it a day today. Extend can be used the same problem. Anyway, anytime you use anything to change an array size, is going to slow down the program. But anyway, changing it to list and will not really help there. In any case, this program will last for a few microseconds, so it doesn't really matter. Anyway, bye for today. Next day, we are going to talk about symplectic algorithms. They are very interesting stuff, but that will have to wait till Monday. Oh, sorry, Tuesday.